All right, we are going to go ahead and get started. Thanks everybody for joining us for the latest installment of This is CDR. I am your co-host, Chris Neidl. I am one of the co-founders of the Open Air Collective, the host of the This is CDR program, which meets most Tuesdays. We won't next week, as I'll say, because I'll be on vacation. But we meet mostly most Tuesdays at 12 p.m. Eastern. And I'm going to pull up my co-host, Tank Chen, who any regular viewers of the show know well. Hey, Tank, how you doing, my friend? Oh, you might be on mute. So what we do on this show, for those of you who are new to it, is it's all in the title there. We think our job is to be able to really show to our viewing public and audience what CDR is, what carbon dioxide removal is, as told by the innovators and experts and advocates that are actually making it happen in the real world. And so most of the time that will be folks that are with startups or other established companies really doing this work across the CDR spectrum. But we often, we're very involved in advocacy. We'll have policy experts on, scientists, and other folks that we think help tell this very fascinating, complex, exciting, and unfolding story of CDR. So, Tank, how you doing? Sorry.
Well, Chris, how are you doing?
I'm good. I always like to ask this: anything on your radar, CDR related, this week that got your attention or has got you excited?
Well, I'm very excited for today's program. There's been a new project that's been talked about in BC in Canada about biosolid to biochar. So yeah, I'm excited to learn more about that.
This is when I was like a 10-year-old kid, if somebody came from the future and said, you are going to be so into concrete and biosolids, I probably would have been confused and disappointed. But now where I am, it is at the intersection of something I find so fascinating. And so really, really excited to have our guest today to be talking about it. So we'll get right into that, and I'll hand it over to you, Tank, to go ahead and introduce in a second. But again, already explained what Open Air is. Please do join the community. Tank will throw a link in there. But today we have Garrett Benisch, who he and I go back a little bit for BioForceTech. He's going to be talking about just their very cool and surprisingly pretty far along company and technology. And for that, I'm going to go ahead and hand off to Tank, who will do the proper introduction, and we'll pull Garrett up on the screen right now.
Thank you, Chris. Yeah, so today we're very excited to have Garrett Benisch join us. Garrett is the Director of Design at BioForceTech and co-founder of OurCarbon. Garrett has been leading the development of OurCarbon and BioForceTech since 2020. As its co-founder, he has positioned this globally unique biochar made from biosolids for applications across industries. Garrett worked at the intersection of government infrastructure and sector ranging from the built environment to fashion to automobile, rewriting the story of waste management in one carbon negative value creation. So what does it mean? Well, Garrett's here to tell us.
Thanks, Take, and thanks, Chris, for having me. Yes, I have to agree. If I looked back at putting a bet on how many times I'd say biosolids in my life, it wouldn't have been anywhere near the number I'm at now, but it really has been fascinating. And I'm excited to share the story of BioForceTech and OurCarbon since I arrived 5 years ago now, which is quite a milestone. It came up quick.
Very much so. So should I pop your presentation up there, Garrett?
Sure, go for it.
All right. Looking forward to seeing the other side. Wait 1 second here. Go ahead and add this. Oops, let me stop sharing mine. That's why that's not coming up. All right.
All right, can everybody see that video going?
We can.
Perfect. So for a little bit of context, this is sort of the scale we're talking about. This is where we're at as a company. And I want to give a little bit of timeline too, because there are sort of two different timelines at play here. So BioForceTech was founded in 2012, late 2012, and developed their technology for market, past full prototype, past pilot into full scale installations until about 2019, 2020, when they opened up a development track for the material itself. So that's OurCarbon. And when I talk about OurCarbon, you can think about 2020 to now. And when you think about BioForceTech, that's from 2012 up to now as far as the development track. So there's a bit of a scale up with sort of a startup idea inside of it. So BioForceTech is based in California. I'm here in our office in South San Francisco with a subsidiary in Italy where we produce all of our units and machines and have operations over there too, as well, just to place some context here for location. When we think about our impact and what we're doing, we have sort of a three-step or three-bucket process: divert, transform, and apply, as is the namesake for the presentation. So I want to go through all three. Some of this will be new information for you. Some of this will make sense if you're in CDR. But it's really important because each moment of how you engage with that part of the process is a moment for different levels of impact. And they really are, each of them provide sort of a different service or a different way of benefiting the planet. So let's start with diversion. This may be a controversial take in this kind of a space, but I do want to put it out there that from our sense of things, both from the market and from the reality of the industries at play, the need to shift over many industries into bio-based inputs, biomass is not created equally. And there is so much biomass out there, but a lot of it is completely new, completely clean, ready for use for things into sustainable aviation fuel, into biopolymers, and producing a biochar from that skips a lot of steps. And I also do believe personally that the market will answer to that these quote unquote waste biomasses are not forever. And so I think in the CDR space, it's really important to be targeting what is a waste today and what's also going to be a waste tomorrow, and how to take space to have value available all the way down the value chain so that we create a biochar blast. And so in that, BioForceTech has really looked at what we call impact feedstocks. We want to take materials that are causing harm today so that diverting them creates an immediate benefit, and that safeguards leaving the biomass available for other uses in the immediate that can be converted down the supply chain into biochar later. And believe me when I tell you that we've started with a true first impact feedstock. So there couldn't be anything more basic in a form of waste than biosolids, and yet more ubiquitous, not governed by the seasons, not geographically bound, and infinitely available. This is a treatment plant in Redwood City, California, serves about 250,000 people. For scale, as we go back in this next shot, I believe, this little system on the right here, that's us. And that's about 1/3 of the throughput of what comes out of this system. So wastewater treatment is a huge process, right? The front end of a plant is measured on millions of gallons a day. And then the back end of a plant is measured on thousands of tons per year. So you have this huge minimization and processing set of steps that leads to two different products that come out of the end of a treatment plant. Water that gets separated, and what you see on non-potable sprinklers and all of that is generally water from treatment plants, and biosolids. The water has pathways, right? Sometimes it's led into waterways as just sort of open outlet of clean water. Sometimes it's reused and recycled, but generally it's easier to manage. The biosolids, that dewatered sludge, which in this case is still around 80% water, is a liability or a burden that must be managed as a waste. So the only two ways to use that or utilize it or manage it today is by landfilling it or land applying it. And both of them come at a different cost. Landfill is pretty obvious when you take, especially an extremely bioavailable organic like biosolids, you cover it up in plastics and wood and garbage. You create an anaerobic situation that allows methane to flourish. Around 30% of biosolids in the US are landfilled every year. Organics in landfill in general amounts to 15% of all methane emissions in the US. And of course, on a 20-year basis, methane is over 80 times as powerful as CO2. So you're emitting quite a lot and you're losing all the value of the material that could have been there. We did a really in-depth LCA, and this is on a carbon avoidance side. I promise I'll get to the removal. But we did a really detailed LCA looking at 3 different factors of how to understand the avoidance that we can achieve by diverting biosolids from landfill. What you see here is the EPA's WARM model for the 4 climates in the US in sort of a large swath way: a cool, dry, cool, wet, warm, dry, and warm, wet climate. That's all based on humidity, precipitation, average temperature, et cetera. If you tune the different climates, and then look at the least digested or most digested biosolids, which would mean there's the most available carbon there to become methane if it's undigested and more raw, or less available carbon if it's digested for methane already. And then if you looked at the landfill regulations in the area to the most regulated or least regulated landfills, you get essentially a set of brackets of what the type of emissions profiles look like that you can avoid. The system in Redwood City in California avoids about 4 tons of CO2 equivalent in methane on a 20-year basis per ton of OurCarbon that we produce. For reference, that's about a car off the road for a year for every ton that we make. And that system you saw is a 300 ton a year. So it's almost a car a day going off the road for a year. Our 2 systems that are in Pennsylvania and in Northern California and Redding are in the cool wet region. That's between 9 and 14 tons. So we average around 10 tons a year. So you're doubling or more of the impact there. If we were to dial all of these up, so we have the least digested biosolids in open landfill in the hottest and most humid climate in the country, you're looking at the American Southeast and Florida all the way through to East Texas. And that's a 24 ton per ton maximum avoidance just by choosing to divert this material from landfill. So we haven't even utilized it yet. That's what it means to be using an impact feedstock from an emissions avoidance perspective. Now, we're in the middle of a grant application due this Thursday for New York. So I want to just zero in on the East Coast because we've been studying it quite a bit. Just in New York alone, on a dry basis, there's 375,000 tons of biosolids per year produced and managed. 68% of that, according to 2015 and 2018 data, goes to landfill in New York. So that's more than double the national average. If we multiplied out the bottom and top possibilities from most conservative to most extreme for those landfill emissions, it's almost 1.8 million tons of CO2 every single year coming out of landfills just from the biosolids just in New York going there. That's almost 450,000 cars off the road for a year if we were to avoid all those emissions. It's a really big savings just by changing what we do with our biosolids today. If you're not landfilling the biosolids, your other option is land application. And there is a beneficial aspect to that in that you have the bioavailable carbon, much like a manure, going in as a fertilizer and some amounts of nitrogen and phosphorus. But alongside of that, you have pharmaceuticals, heavy metals, microplastics, and most recently brought to light and regulated is PFAS. So these are the forever chemicals originally found in Teflon, now found in all stain-free clothing, waterproof textiles, easy to clean furniture. If you look for, Gen X or C8 in your paint, that makes it longer lasting, et cetera. Even optical brighteners in toilet paper have PFAS in them. And we're finding that it's in the biosolids as well. This is just a sampling of headlines that are going around from everywhere from Nebraska to New York and other states. So it's really across the entire country that this awareness and the lawsuits that follow are coming. And this, just as an exercise to prove the point, is looking at one New York Times reporter from December to May, so just 6 months. All of the headlines that are in brown are specifically to biosolids and PFAS. This is all the PFAS articles in general, and the list goes on. So it's really receiving quite a lot of press, and understanding is growing, and the regulations are following. Looking at Safer States, which is a bill tracking website, you can see that 35 states have put over 200 policies introduced, with the majority of them already adopted, regulating PFAS in general, drinking water, manufacturing, production, use, et cetera. If you zero in on biosolids, 14 states have introduced 20 policies, and 5 of them have already been adopted. Maine outright banned the land application of biosolids in 2022, and this year both Vermont and New York put forth bans. New York's is a five-year ban that's on the table right now, and Maryland is starting to set concentration limits in sewage sludge. So in the entire East Coast and Northeast seaboard, you're seeing a lot of movement stopping land application of biosolids. So what do you do, right? Right now, wastewater treatment plants are paying haulers that are in the middle, that are bringing it to these different places and paying fees to offtake the material and put it somewhere. And as the concerns about lawsuits, the concerns about contamination come up, so do the tipping fees. And all of that is going to the taxpayer. So it's our money that's paying for this burden to be managed. That's what BioForceTech hits at the heart of and changes, right? So BioForceTech diverts biosolids from these current practices, transforms it into a PFAS-free material called OurCarbon, that's carbon negative, and then applies that to industry. And that's what business model has allowed us to grow to date. So here's an example plant. This is in Redwood City, California. We have 3 biodryers and 1 pyrolysis unit. That's the 2 types of machines that we produce that are working together here to handle about 65,000 people's worth of biosolids. It's 3,000 tons per year that outputs 300 tons of biochar. When you put them together, you can take 10 tons of dewatered biosolids at 80% water, 20% solids, and output 1 ton of OurCarbon. So that tipping fee, even if you're managing it the same way, is now 1/10 of what it was. The PFAS contamination in the material is absolutely eliminated to non-detect levels or 0, whatever the detection limit is possible so far, we've eliminated. The tipping fees have been turned into a profit share, so we're actually managing the offtake and sharing a small profit back to the municipality. And we've turned biosolids management, or the biosolids burden, as I like to call it, into a material production site. So let me take you through each machine really quickly. The biodryer is what enables the energy balance and the carbon balance to happen. When BioForceTech started, they looked at drying biosolids using natural gas or standard techniques, and then undergoing pyrolysis to make biochar, but you simply couldn't do it without expending more carbon just to dry the stuff out than you would sequestering in the material. It takes so much energy to evaporate water that the balance just wouldn't work. So the founders of the company said, why don't we look at biology instead? And that's what the biodryer does. We essentially have a long container with a perforated floor that is represented here, and an air unit that exchanges air back and forth from inside the unit to air outside and exchanges the heat. We have 5 gates that open up and fill 8 tons of material at 20% solids, 80% water. It's known in the industry as biosolids cake, which is just a wonderful term to walk away with. Once we have the 8 tons of material in there, we pass normal air from outside through the bottom of the material up to aerate the biosolids and let the bacteria already present in there flourish. I like to say that we're like a nightclub. We get the booze and the music right, and all the dancing is what makes the place hot, right? So it's not biogas, it's not external energy. We're just maintaining the atmosphere that's in there for the bacteria to flourish. The temperature increases to about 150 degrees Fahrenheit, so it's not very hot, but we have a heat exchanger that's custom to us that allows us to exchange that heat back very efficiently into the incoming air and create a feedback loop that maintains that 150 Fahrenheit with extreme precision. At the end, it gets a bit too dry for the bacteria and they go dormant. So we do use external heat in the end if you just have the dryers to finish off the drying. From this drying, we can kill off certain pathogens, Salmonella, E. coli, things like that, and move into a class A biosolids from a class B, a higher quality biosolids, and your 8 tons have become 2 tons. So in this case already, at 30% of the normal energy load and time competitive, you have quite a mass reduction on your biosolids. And it just runs in that batch process over and over again. Once you have dry solids, then we can unlock pyrolysis, right? Biosolids is already a lower carbon material, higher ash material. And so it has a very low heating value, and doing pyrolysis of biosolids, 100% biosolids alone, not co-processing with wood or other things, is very difficult. And so you really need it to be at least 80% dry for the input. This is our Sigma pyrolysis unit that allows that to happen. It's named after the Sigma bond between carbon molecules. It's the most basic and strongest bond. And it's a high quality pyrolysis unit that unlocks a hybrid technology that I'll explain. Basically, for those who don't know pyrolysis, just very quickly, if I took a piece of paper like this sticky note here and I lit it on fire, the carbon in the material would bond to the oxygen available in the air and form CO2, and you get a flame from that energy release, right? That's what we know as burning. What's left over is ash, which is the mineral content that would not evaporate or volatilize either way. If I took this but put it in a space with no oxygen present and heated it up to those same very high temperatures, in our case 650 Celsius, the carbon that is volatile and available quickly will bond to the hydrogen, nitrogen, and oxygen in the space and in the material until there's none left, and that forms a gas, a mixed hydrocarbon that we call syngas or synthesis gas that we can use to create heat. So we direct that off. But the bulk of the carbon and the ash that would have been left over anyway gets bonded and fixed to itself because there's nowhere else for it to go. That fixed carbon bond is that carbon removal, right? That's where you're stopping it from being in that fast carbon cycle anymore. And depending on how well you do it and how much carbon is present is how you can calculate the permanence and the amount of carbon and CO2 equivalent that is removed. So with that primer, let me explain how we do it. We have an air inlet here that brings air from outside through this piping around the wall that separates the reactor where the pyrolysis actually happens, and then feeds back into our oxidation chamber here. We heat up this oxidation chamber first with natural gas. This is just a couple of hours to bring it to those high temperatures to get those conditions to form. So we'll start it up like a big stove basically, and bring that heat up to temperature through the wall that will heat up this clean air from outside that runs through around, again, the wall of the reactor. So the air is separated in all these spaces. Once this is at our 650 Celsius, we can feed in dry biosolids from the biodryers until it hits those pyrolytic conditions and kicks off that syngas. That syngas can be utilized with the negative pressure so that it's always drawing that way from the heat to create enough heat to keep the system going. So we're burning the syngas here in a controlled environment, sending it off to our scrubbing unit that's permitted and scrubbing all the emissions to heat up enough air on the outside to keep that process going and maintain the system. We only need about 20% of the heat from the syngas oxidation to make that happen. So the other 80% goes to a water loop that we can share back to the biodryers to eliminate that need for external energy on the biodryer side. So when I said that it's 30% of the normal energy load for drying, that's if you only have dryers. With the pyrolysis in tandem, the entire thing eliminates any need for thermal external energy when you're processing. What comes out is free of contaminants because of the high temperatures and amount of time. This is 650 Celsius for about 15 or 20 minutes. And it's carbon negative because of the amount of fixed carbon and the unique mineral content that's in there gives it new uses. So to put all that together, we have these batch dryers that we always load in sequence so that they're unloading at different times. So we have constant flow of material. They're doing their thing, honestly, very quietly the whole time as compared to continuous processing dryers that are at higher temperatures. Once we start feeding the Sigma unit, that comes to temperature, puts out our carbon that we offtake, and heats up the water in the loop that we can send back in exchange for more hot air to make the whole process energy neutral. So this is sort of the ballet that forms once it's all working together. And here it is in action. So we have the 3 biodryers, 1 Sigma pyrolysis unit. This can be done in units all the way up to multiple dryers and multiple pyrolysis units. I'll talk about how we're right-sized right now. But this is how they get loaded. These are the 5 gates. This is what it looks like when it's drying. It's very quiet. I can talk to you at this volume. There's really not much going on. Every couple of hours, the dryers will rotate to move the material around. That's the actual rate that they spin. It does 2 rotations every few hours. And then we unload into this conveyor belt that you see down below out of the first gate into a hopper to have material on deck to then feed the pyrolysis unit. Here's the hopper that goes in, and then the reactor unit is right here. You're looking at the nose of the reactor over here. It comes down through at 650 Celsius, and here's that syngas pipe that kicks off into the combustion chamber, the oxidation chamber. That flame is 100% syngas produced, where we then feed the heat back, output OurCarbon, and have it for offtake. It goes up a 45-degree screw to cool with some quenching water. And what results is this super sack, which would be about 1,000 to 1,200 pounds, that used to be 10,000 to 12,000 pounds of raw dewatered biosolids. We were studied specifically by the EPA and published to be removing PFAS to non-detect levels. This is in the material itself, the OurCarbon output, in the scrubber water, in the filtration media, and from canister testing in the stack emissions as well. There was not yet an approved method for the stack emissions by the EPA, although it was a standardized method because we were the first ones doing this. Stay tuned for the next couple of months. We've been working with an engineering firm, third party, for multiple testing sites on our system, and are really excited to be at the edge of this to understand more of what's happening there. But the material itself coming out is certified for use in baby clothing and food containers. It's so clean. So I can assure you that the material itself is definitely PFAS free. We've been permitted in the Bay Area Air Quality Management District, which is one of the most rigorous air districts in the world. It took us many years to get there, and we're really happy to stand on the shoulders of that emission scrubbing and know that we have a really, really clean output from an emission standpoint as well. We're USDA certified bio-based, and our fashion inputs are classified as Oecotech Standard 100. So baby clothing, things like that is all able for use for us. We're right-sized to about 80% of the market in the US, 1 to 15 MGD, 1 to 15 dryers, which would be 1 to 5 or 1 to 4 pyrolysis units, or about 300,000 people per system. And we would install directly at treatment sites. Here's our factory in operations in Italy. We're building these units as fast as we possibly can. We have over 18 installations with 34 biodryers and 3 pyrolysis units running between Italy and the US. I'm going to change that number to 4 because I'm excited to say that we have the first Sigma in Italy starting up right now. I actually received a video this morning of it working. With our contracted biodryers in production, we just passed 50 biodryers, and we have an 8 dryer and 2 Sigma unit system in Brentwood, California, going in at the end of next year. Here's our Sigma 1 in Italy that was just unveiled about a week and a half ago. And that's now in startup for a special permit for 1 year to sort of set the spec for the country because they've never had biosolids pyrolysis before. And finally, we're leveraging this precision of the technology. So this is our bench scale mini Sigma, as we like to call it, where we're making designer carbon. So that ability to completely control temperature and residence time and have such a tight throughput allows us to create what we call designer carbon. So what you put in is the biggest shift in what biochar you get out, but also how you process it by time and by temp will dictate different aspects of the biochar characteristics. So we're building a master database. We're partnered with the USDA. We're working with agricultural producers, with different waste biomass producers from everything from pharmaceutical to other sludges to understand how we can make carbons for all different markets with biosolids and outside of it. So get in touch if you're interested in processing a biomass or proving PFAS destruction through this system as well. So here's the stuff. If you're familiar with biochar, this is not what other biochars look like, right? This is a very different material that we classify as a carbon negative base material because it goes into so many different applications. So finally, we've transformed. Now we can apply. And there's a lot of different applications. I want to focus on concrete given the topic today, but it would behoove me not to breeze through a couple things as well. So on the concrete side, OurCarbon is uniquely lower carbon, higher ash, and has a specific morphology that allows it to be mixed into structural grade concrete in the place of aggregates like sand. That means that we can put hundreds of pounds per cubic yard into the material as a durable carbon storage. At a base level, we are not replacing cement. And I want to be totally clear on that right from the beginning. There's ways that we can, and I see us working in tandem with other technologies and other ingredients to have ultra low carbon or carbon negative concrete, thanks to us and other uses. But carbon storage in the built environment is its own sort of topic. Here's our EPD proving and published that we have this carbon negative output. This is based on years of production data and electricity data from our plant. We have enough carbon in here to sequester 1.1 tons of CO2. It's about 30% carbon, the material, because of the makeup of the input material. Only 0.08 tons of CO2 is emitted per ton of production, leading us to that negative 1.02. That's an extremely small processing footprint, even for pyrolysis that's creating heat. So again, the biodryer and the pyrolysis working together really enables that really low energy footprint. So the built environment needs to decrease their direct emissions, right? And that means reducing amounts of cement. That means eliminating steel when it's not necessary, et cetera. But the building environment also, I would say, has an opportunity in their building mass to durably store massive amounts of carbon alongside their own reductions. This is a study from UC Davis that was released in January, looking at the building mass of new construction year over year and finding locations to store carbon in that mass, and found over 16 gigatons of storage potential in the physical mass of new built environment. That's half of our entire global emissions from 2021, just in the built environment alone. Of those 16 plus gigatons, 10.5 of them is replacing concrete aggregates with carbon storing materials. There's simply so many rocks in buildings sitting underneath us in the foundations, in the walls, in the columns, forming the aggregate for which the cement binds into concrete, that there's a massive storage potential, really most of it, when you're looking at different building systems. So that's what we're doing alongside other companies that are creating these sort of aggregates that can store carbon in the environment. And we've been doing this at scale. So this is a field trial we did with Central Concrete. We have extensive testing of how the material behaves at different dosages in different mixes. And we're testing alongside the material we're producing at all of our plants as we pour projects. We'll take fresh samples, slump, core samples, and make cylinders for testing for strength. In the lab, we've done chloride, we've done freeze thaw. We've mimicked many, many years of different freeze thaw cycles to make sure the ice doesn't expand in the material and break the concrete. And we're seeing really good durability results. Here's an example of a campus pour that we did recently with Skidmore, Owings and Merrill and Central Concrete, and Carbon Pilot did the MRV on this. 2 different mixes, same dosage, 76.5 pounds of CO2 and 76.5 pounds of OurCarbon per cubic yard. That was actually meant to be 100. We learned a little lesson on dry weight versus saturated weight between concrete plants. So the material holds so much water that's the dry weight that ended up in there. But you can see we have a big reduction on the percentage of the original EPD, the original GWP, just from the use of OurCarbon. In other mixes, I'm not sure if my camera will be on with the shared screen, but what I have here, I can hold them up after during questions, is 2 6,000 PSI mixes. These are higher density, higher cement, but also higher OurCarbon, where we've eliminated 60% of the carbon footprint by storing the carbon in there. So we don't have carbon crediting in our business model. That EPD is where the carbon benefit remains because we haven't put down our systems for the sake of the carbon credit. So we developed the system that delivers a service of the volume reduction to the treatment plant, and then we have the carbon benefit available to be calculated directly into the concrete. So the very building you're standing on is where that carbon is accounted for across the entire supply chain. And that's very unique. Here's some video from that pour, also proof that everything looks good in slow motion. The placement, the pumpability, the curing time, nothing was really altered in how the material behaved, partly because it is simply an aggregate swap and not a novel new binder that changes sort of the whole chemistry of the material. So it makes it very deployable. Solid Carbon was one of our first users, if you know them, and hats off to Michael Bernard and John Mead, using this material in Oregon in the Burnside Skate Park. The first project that we did together won an NRMCA award as well as another one. And together there's about 10 to 15 pours in the ground today, all structural grade concrete. And Washington State University professors have also worked on ways that we can leverage and double down on the impact. So biochar holds a lot of water, right? If you can absorb water that has potential cementitious in it, like concrete washout water, which is another pollutant that needs to be managed, you now have our biochar embedded with cementitious materials that would have gone to waste. So that's what they did. They soaked concrete washout water with our material to absorb it and then used it in the new concrete pour, which allowed them to reduce the amount of cement coming in and create a concrete matrix through a binder matrix through our material that made the entire mix stronger, still with our carbon storage delivery. So I see this as an ongoing process where we'll be developing and co-developing across other technologies to help bring in benefits to concrete. We have also pigment uses, and I'll go really quickly for the sake of time and because I know the focus of this is on concrete. But I'm wearing Virus's Rethink Black ink. It's fully commercially available. We're replacing carbon black here, which is the black in everything from mascara to car tires to your computer keyboard. This is our famous shirt that I'm wearing today that helps describe where the material comes from in a little tongue-in-cheek way. And we've worked with different fashion designers and groups. If you're on the East Coast, Print Natural in Philadelphia prints exclusively with Rethink Black that has OurCarbon as the pigment. It's 100% water-based, 80% bio-based ink. Model Number is another one of our partners that's 3D printing full-scale furniture. We're able to keep them bio-based because most pigments are synthetic. And so if you have a PLA bio-based polymer, you want to keep yourself bio-based. So together, we've done full-scale projects. If you're in Williamsburg, the Domino Sugar Refinery, beautiful new office building inside of the skeleton of an old Domino Sugar Refinery. The whole lobby is model number furniture in OurCarbon black. And that's sort of just the tip of the iceberg. I have here bio-based compression molded plastics from Rayome Materials, a Texas-based group. This is a bio leather from them, colored with OurCarbon. Viba is doing injection molded polymers. Covestro, these are dashboard samples. Here's a bio-based polyurethane shoe outsole. So this opens up quite a lot of space for a whole new category of material input that's carbon negative. So to wrap up, I want to share an exciting opportunity or exciting moment for us. This Thursday, we are finishing our submission for our finalist project as in NYSERDA's Natural Carbon Solutions, Challenge Area 2 for Innovations in Carbon Negative Buildings. It's a two-track project that's going to show the feasibility of developing this material supply chain in New York specifically. Track 1 is what you would expect. We want to pour concrete with OurCarbon, and we have partners on board that are from large-scale firms that we're going to pour concrete during the 2 years that uses the material we've already been producing in Pennsylvania and California to bring it into the New York market and get it in the hands of concrete producers and architects and people. Track 2 is going to use that bench scale unit to collect samples from as many treatment plants as we can. We're hoping for around 15 to produce biochar, analyze the biosolids, analyze the biochar, test for PFAS removal, and then take that material and send it to our partner lab, Braun Intertech in Minneapolis, that will test all of those biochar samples in concrete testings in cylinders to get a huge data set of how the material behaves in concrete to show that this can be done across New York State. So it's the biggest study of its kind. I'm really excited to be working on it. I hope that we get it. We apply this Thursday, so it's 0 hour on this project. But it's really exciting, honestly, even to be a finalist and to see the nod to this possibility. So that's a lot of what I've been working on, is really taking two sectors, the wastewater sector and then the construction, architecture, engineering sector, and introducing them to each other and showing them there's a new way for them to play together that this technology enables. If you want to learn more, head to ourcarbon.co to learn about the material, bioforcetech.com, and please feel free to send me an email. Looking forward to answering your questions and bringing this along further. You're muted, Chris.
That was just brought together so many things that I'm interested in, and you landed it in New York, which by itself is interesting to me. So many things to discuss here that you brought up specifically in reference, but also points to a whole other continent of impact around the intersection of building materials and carbon removal and storage, and the other value that's produced by achieving that. And it just was incredibly exciting. I think we also have the fact that, you've been with the company for 5 years, but the company is older. And just in more general terms, a lot of the companies that we have on here are obviously much newer. They're at an earlier stage. And we always sort of reflect on what's in the near future, but you guys are in that future to a certain degree. You've built a lot of things. So even from just the general point of what, how these solutions can really evolve over time, you've given us a great example of that. So many things to discuss. Tank, this is right up my alley on like 800 different levels. But just curious if you had any remarks to make just from your first impression.
Yeah, no, it's very impressive in the way you explain the pyrolysis and in general how it all works, the whole process. I think, I've never heard it, how it works, and it's just very interesting to see how this is integrated with wastewater treatments and how there's a similarity in the wastewater treatment infrastructure in general globally, right? So the potential to scale is there. Yeah, that is very exciting.
Yeah, Carl is one of our most diehard open air members who participates meaningfully in almost everything we do, and he's here every week, based out in the Bay Area. So maybe he can get a tour but gave you a shout out, and I agree with him. Just in general, your presentation, the visuals, I think you'd get the Academy Award in terms of who he had there. And that actually kind of links to our first question, which we always start off with, just a little bit about you. And I know a key fact that you're a Pratt alum, and I think we could see that reflected your artistic touch to this presentation. But we always like to kind of know the backstories of the people who are presenting, that there are real people that are making this happen. So yeah, tell us a little bit about, how you got into this line of work.
Yeah, and let me, just for fun, there we go. Sorry about the sound there. I'll drop in the chat here. I think, Tank, you can share with everyone, but this is, if we want to go back to a younger, sprightlier Garrett, there's a video of me presenting my thesis from Pratt that's centered around this in a much more nascent way. I actually come from a background of fine arts and industrial design. So my interest is really in making things a material process. I moved from a fine arts bachelor's to working for Mass Design Group, which is an incredible nonprofit architecture firm doing really amazing work in Rwanda and Haiti and other areas. And I worked with them on building production from local producers in Rwanda that was just gorgeous and made of local materials, and sort of scaled up there okay, I can make one pretty thing, we can make an entire interior. And I came home with actually this amazing portfolio, but not even the ability to make a construction drawing. And so I wanted to know, how do we make all the toothbrushes, right? How do we scale material usage and shift that? And so I went to Pratt for a master's in industrial design. And my thesis project is called Some Waste. It's a pen and ink that could be produced from biosolids, both the pigment for making a biochar and making a biopolymer by feeding biosolids to a bacteria that would make a PHA, a compostable biopolymer, with the goal that you would end up writing on your hand or chewing on your pen and remember where this material comes from, and it would shift sort of society's feelings around waste and use something that New York's paying millions of dollars a year to get rid of. So if you asked me if that was commercializable in 2019 when I graduated, I would have said probably not. It was more to showcase my brain and what kind of space I wanted to work in. And then I had the honor of seeing BioForceTech present at a biosolids conference that summer when I was just sort of seeing what's available there in that industry. And here was this group producing this material at scale that I used for the pigment. So as far as takeaways, you may think you've got a nutty idea, but you never know what's really already out there being developed. But that's how I came here, from more of a creative space. And I think a lot of the designers are called specialized generalists. A lot of it is translating, interpreting, understanding, regurgitating in a way that's digestible to these different groups. And so it's been really cool working with government, working with fashion, working with concrete, with all these different people that are really trying to get the same thing done, but using different words and with different levels of understanding. So I find myself as a bit of an interpreter.
Yeah, we just were the beneficiaries of that ability for the last 25 minutes. And you went to Pratt, which is one of the most storied art and design schools. We've established too. I used to live right next to it, yep. And we probably were standing in line at Luigi's Pizza at one point, which is the best pizza in New York City.
For sure.
But let's now switch to. I just want to sort through all of the different things that have been raised here. The first thing is about, if we were to scale. I wasn't familiar with that UC Davis paper, which is amazing. That escaped my attention. Just to give people a sense, if that bears out in reality, 16 gigatons of storage annually. Okay, the IPCC reports estimate on what we need to do by 2050 per year in carbon removal globally is 10 gigatons, right? So that is a massive number. So I'm going to reach out to the authors of that and find out more. I dropped a link to that paper. And it's also not about one thing. It's about many things that can be blended into, the built environment, whether it's an aggregate, a new form of cement, or curing things with carbon. To take your technology in that, can you give us a sense of proportion here about if you were to sort of be able to magically scale your solution across all the wastewater treatment plants and use those biosolids? What's the kind of impact we would see?
Yeah, so for sure, this is I would say a first material type that unlocks a new investigation. So let's take New York, for example, right? 185,000 tons of aggregate is not a lot compared to sand, right? But also this sludge type is not as unique as you would think. So there's other industrial processes that have sludge production that's similar carbon content. So where a lot of people are moving from the biochar space, from the highest carbon, highest quality in that space down, we're actually moving from this space up. And so we have about a conversion factor of 1/2 to 40% from biosolids to biochar. Is there 32 billion tons a year of biosolids on a dry basis? I don't think so. But and is that located, scalable, correct to all the markets? Not positive. Can we transition this waste and use this to set the stage for how we would investigate all sort of sludge outputs and how we process from now on and go into concrete to aggregate that? Absolutely. And should we be, mixing biochars together, creating new products out of that too? Absolutely.
Yeah. And I one principle I have to just sort of back out of how I posed the question, when this has been kind of a motif over the last several weeks and even longer, Garrett, is that with carbon removal, we have so many different ways of doing it. And it's never about how does this one thing stack up against need, because it'll look sort of small, but it's more that we need to get into this widespread, deep sort of habit of more saying, what is a thing in industry or resources, and how do we explore that for the maximum carbon removal that it can achieve and party with other things? And I think this is a great example. What else do we want to do with sludge? There's things we can do. So if we can start creating value while taking carbon out of the air, that's really significant. We have some good questions that are coming in from some real concrete heads and regular friends of Open Air and members, Sue Dorward and Harold, they're very, very practical questions. So we'll ask those in just a couple moments. Let's talk about a couple of things did come up, I think, that are really interesting. So I'm excited that this is New York, obviously, since I'm from and based here. As you know, there was controversy about a year ago. I'm going off script here a little bit, Garrett. But,
yeah, that's okay. I know what you're going to say.
Where upstate in Saratoga, which is just about 45 minutes north of Albany, there was a proposal to do a sludge to biochar plant that ultimately had a lot of community resistance and was basically killed. I could already see the differences, vis-a-vis the sources of controversy for that program or that project proposal for what you're doing. Would you be able to kind of, because you know that one well too, do you want to sort of draw some distinctions between what you're doing and what kind of was the fatal death of that project?
Yeah, and I think all efforts are applaudable, and I don't want to say that there was anything necessarily wrong with that proposal, but I can see why the pushback emerged. I don't know, so don't quote me on the numbers, but I do believe the intention of that was around 700 tons a day of input biosolids to that location in Monroe County. We process about 15 tons a day per Sigma unit of biosolids that the place is producing, right? So 700, let's just talk scale of what that would do to a community or what that would do to a given location. A lot of groups have attempted capital projects that are trying to act as sort of a biosolids refinery that take on this massive amount of biosolids. And not only do you have so much input capital on the CapEx, OpEx once it's up and running, but also the sheer wait until it turns on to know if it's even going to work, and the amount of emissions you're working with, et cetera, is just very different. It's a really big challenge. We're really happy with a model that has a resilient distributed grid of production that's at the treatment plants, taking care of the same biosolids that your taxpayer money is costing you to manage currently. So it's a very, very different model. The Saratoga project, from what I understand, did not have a technology to present. And so they have no permitting history, no production history, et cetera, as well. And again, just the sheer volume is completely different. So we would, love to be producing locally, regionally, across all locales and regions, rather than creating a sort of hub for the entire Eastern Seaboard, where you're going to have massive amounts of trucks bringing material there.
That was the huge difference. It was the transportation thing and the dislocation, and the way that you're more embedded close to the actual source is the absolute critical difference. And they didn't have the benefit of the kind of presentation that you were able to give, not only showing this stuff real, but, when people hear, poop and this, they just, sometimes there's a visceral reaction, I think, and they're not able to sort of understand what is actually going to be happening. So that's why I'm really glad that you're doing it in New York right after that, in a way, because it gives a very, very different look to the subject. So I think that's
well, fingers crossed. I appreciate you using definites, but We submit on Thursday. We'll hear
that's
back
another
soon.
question too, which maybe we have moments we can think of, how do we sort of help this, kind of happen here? The other part is with, I am interested, as I alluded before, is that the 10 years, I can't remember, tell me again, Garrett, when the company started?
Late 2012.
Okay, so that's a long time ago, right? Certainly by anything CDR standards. And I am just curious about, from the initial concept, whatever that looked like in the early days, to where you are now with deployed units and, what you're doing. What are some of the kind of twists and turns or pivots or big learnings that the company, sort of absorbed that helped change the sort of the direction of the company, if any at all?
Yeah, absolutely. So the founders came over from Italy, from northern Italy, outside Milan, to Silicon Valley to after attempting in Italy to get the technology to take hold as a concept, at that actual startup level. The cost to manage biosolids was just too low in Italy at the time. So they came to an area that has the regulation, that has the interest in sustainable infrastructure, et cetera. And really, hats off to Silicon Valley Clean Water here in Redwood City that gave them a space to develop all the prototypes. All of the pilot facilities have all been here in Redwood City in a partnership with the treatment plant here. I would say the biggest pivot is that a couple of years in, agricultural use of biosolids became banned in Italy, and the cost to manage the sludge skyrocketed. So we actually saw rapid uptake of the biodryers first. Again, there hasn't been pyrolysis until pretty much today of biosolids. So the biodryers first has that 75% mass reduction in Italy. And then, understanding all the ins and outs of really getting a unit to work, working with the market, knowing who signs off versus who actually gets the check to happen, right? This is a coalitional technology where the costs on different sides are strong. I mean, it's a real technology. There's real regulatory pressure. There's slow capital projects, taxpayer dollars, municipal oversight. So I think getting to know the permitting, getting through these baby steps that can be a valley of death for big startups, a lot of it has been, I think, slowing down pacing and understanding this is the only way to get it done is to crawl. And so I think I can assume that before I even started, the rate of uptake and rate of innovation from what we can do versus what can actually be done on the ground with everybody involved to bolts on the ground and material starting to process, it's slow. And I think a lot of people run out of burn from their investment structure, the way that they're trying to grow as fast as an app company. And so I think, hats off to BioForceTech on their growth strategy on just doing it slow, doing it right, measuring 3 times, cutting once, recutting, et cetera.
Yeah. So I have one more comment real quick, just to kind of frame for people. Then one more question I do want to get to Sue and Harold. You should meet both Sue and Harold too. I will connect you to them separately. They're both very much on the ground, active in the space. One thing I think is really exciting, and I put it in there, is that concrete is almost, you can kind of look at it like a butcher chart, that there's many different ways that you can decarbonize and store carbon in different parts of it. And what you're going at is kind of like the holy grail to a certain degree, because aggregate normally is in all mixes, really, or most mixes, most of what it winds up being concrete is gravel and sand. So if you're starting to put that into a concrete mix of something that's carbon negative, but it doesn't preclude the possibility of these emerging novel cements that are coming that are either ultra low carbon, no carbon, and some are even flirting with carbon negativity. We are looking at a future where this most common building material on Earth, second most used material after water by human beings, which is its main ingredient, cement, accounts for about 8% of global emissions, which if it was its own country would be the 3rd largest emitter. Converting that over the course of time into something that could actually be a net sink. So I just want to kind of let that sort of sink in for people, no pun intended, is really significant. The other thing was the other thing I really like about it, we just look at it from a relationship, sort of who your customer is, value chain part. You're not talking about you're talking about one kind of partner or customer to potentially deal with, which are wastewater treatment plants. That a lot of those are municipally managed or county managed, and they might be in places that have emissions reduction. And so rather than selling to a variety of different types of customers in a fragmented market, you can kind of model a particular target, at least on the wastewater treatment side. The concrete one is a little bit different. So I didn't know if you wanted to comment a little bit about what that's like to engage with the wastewater treatment world, as a partner / client.
Yeah, and it is, in the end of the day, in the current model, the wastewater treatment plant is buying the system and operating it, and we are off-taking. So it's truly a handshake, right? It's not access to their land for us to just run our stuff. It's their technology, and we have an off-take of the material, but we've supplied it. So it really is very collaborative. It's all, at the end of the day, there's a lot on their plates, a lot on a mayor's plate, a lot on a governor's plate. And so dollar per ton and payoff over time with a factor for fear of the regulation increasing for PFAS, for landfill avoidance, for the emissions goals of the state. That's what's going to drive everything. And then does it work? Does it turn on? And so having systems on the ground that we can tour people to, say, here's the stuff, having projects in the ground in concrete, and having that offtake be reliable, that people know we're going to get it off their plant, is really important. There is it's a slow adoption rate of a space. It is a proof in the pudding. I want to walk around. I want to kick the tires over and over again. I want to know that my biosolids is not different than their biosolids over in Silicon Valley. So, this project in New York, if we get this grant, can really, it's the largest first of a kind study at that scale of a breadth of biosolids that would really prove out that model to get rid of a whole set of kind of checkpoints or excuses on the way in.
Yeah, let's make that happen, man. Well, we can go a couple minutes extra if you can, Garrett. I don't have a close this week because we're not on next week. So let's get right to the questions. Where should we just do it in order, Tank?
Yeah, I think so. Let's do it in order. So the first one from Sue, geographically, where is your material available to be used as aggregate today or soon?
Yep. So Bay Area, Northern California, Central Pennsylvania.
Okay, fantastic. Sue is a titan of the field here. So you should definitely connect. And the next one, I'm going to put up Harold, another one who runs a grassroots group called the Blockheads, which are citizen activists focusing on decarbonizing concrete. We got there.
So what is the cost of OurCarbon aggregate needed per cubic meter of concrete, say, for a typical sidewalk pour? This is ballpark.
Yeah. So, and let me just to answer Sue as well. On pilot projects, we want to set the stage in different areas. So that's where it's available, where it's being produced. If you're in Milwaukee and we want to do a project that
he's in New Jersey.
Oh, great. I'm from Jersey too. So you're right nearby. But in general, for people listening, if there's someone in the middle of the country, someone in Canada, and we want to, prove and have a pilot project, we can move material for that. Obviously, the impact is obvious. For costs, so of course, I'm not going to tell you the cost, but I would say that we relate our cost per pound on a cost of drawdown per pound on the overall GWP of a building. So if we're talking concrete aggregates, sand is $13 a ton and we're running out of it and nobody's talking about it. So that's a whole different topic. But if you look at a library that you're building as a campus organization and you need to bring down the GWP, concrete is the cheapest part and the largest carbon footprint of the building. And so it's more relational to, do we switch everything to mass timber and trust that carbon removal associated with that? Do we offset everything away from our project, or do we pay to make sure that the GWP reduction is in our project? And that's how the cost is factored in and modeled from the building owner, the developer, the architect, more than the commodity market.
Tag for time, I think we'll skip over Harold's second question, but I can get him the answer for that. Do we want to go to Niran Chana?
Yeah. So the next one, do you have any experimental readings available for biochar composite on how much carbon it holds?
Yeah, so every biochar has a different amount of carbon, and you can put a different amount in depending on what you're making in general. Our material is pound for pound carbon negative. So if you can add a pound, you'll sequester a pound into there. So we have projects in the ground with anywhere from, as far as concrete, from 100 up to 200 pounds per cubic yard. This is sort of our max ceiling. That's 300 pounds and a 600 pound cement mix. So it varies, but that's some estimates for you.
Excellent.
Next one, government policy seems critical in your space. Do you do any policy advocacy work? If not, are there any groups that are advocating for policy that will help you scale?
Yeah, Chris would help. No. Yes, absolutely. So we're a small team. I totally am happy to say I need help. The policy can be integral. And what's really interesting about us is that we are straddled across a lot of sectors. And so sometimes we don't necessarily fit into a direct category, right? In the world of biochar, we failed as biochar for a very long time because for fear of bad pyrolysis, biochar had to be 50, 80% carbon or higher because everyone assumed we were processing wood. So there's a lot of policy out there that doesn't include us or used to exclude us. We've expanded the categories in a lot of different spaces to include us or include us as a building material, let's say, even though we're not from construction demolition waste, right? So it's proof that this rewiring is what needs to happen. This is the silos incarnate, right? If the policy is being driven this way, but we do need someone to say, hey, asterisk, what about BioForceTech, right? In these policy conversations to open things up. Very, very quick, fun takeaway. When I was in New York for the NYSERDA grant, I was in an industry and working group with the government about their construction demolition waste, and a group from the New York Town and Gown and EDC, DEP area told us that they changed their program from CDW, construction demolition waste reduction, to urban resource recovery because of our technology.
Oh, that's
so this is, this is a circular city model that decarbonizes the built environment, but doesn't come from the built environment.
That is super cool, Garrett. You didn't tell me that before, that, we love it when we see definitional changes based on, people seeing real life examples. I think we can do the last two here that were already asked. Okay, if we start with the PFAS one there, just because I think this is really important.
Yeah, so in the process, how does PFAS break down, and what does it break down into? Are there any issues with permitting or emissions?
Yep, great question. So to the best of everyone's knowledge right now is that the PFAS molecules volatilize into the syngas and then travel away from the material into that oxidation chamber. Our specific temperature, residence time of that syngas oxidation chamber, and the turbulence of it are all based on literature and findings to break apart and destroy the molecule into its constituent parts that are harmless. Like I said, we have been volunteering our technology for this. We really have our necks out and are proud of it, working with the EPA, working with third-party engineers to test this. And so we're at the edge of it. At the moment, we're not seeing that it's going out into the air, et cetera. But it's an open process, and this is the update today.
Yeah, and I'll just say with that, Garrett, just my knowledge of the activist landscape in New York State is many of the grassroots folks that came out that weren't just from the community in Saratoga, but were from upstate. A lot of those activists are involved in like beyond plastics, PFAS concerns. So it's just, again, an interesting link that we'll want to make sure is well understood as the data is clear.
Yeah, and if I can add on that, if you look up pyrolysis, it's either kind of big old fires of wood kind of a thing out there that comes up first, or pyrolysis of plastic for aviation fuels and things like that. That's really different too. That's a lot of PFAS, a lot of UV inhibitor, like all the stuff that goes into bioplastics or into plastics, that's being pyrolyzed. Our system is processing something that has a very low amount of PFAS relative to that. And so there's some volume, tonnage, understanding, like just differences in general between the word pyrolysis and what we're doing.
Yeah.
So you can get a scared Google really easily.
Yeah. Last one real quick, which let me just squeeze this into a question that you can answer. So just real quickly, I just want to be clear that at least in the instance of OurCarbon, we're not talking about biochar being used as a supplementary cementitious material or as a cement. So you guys, it's assumed that Portland cement, under current circumstances, this will be biochar plus Portland cement. But to look at the second part of the question, what do you guys kind of use as your frame of reference about the storage? I have my own answer for that, but like how long is carbon stored in biochar that's in concrete as an aggregate?
Yeah. So I will say, most of our pours are using type 1L cements. They're using fly ash and slag. They're not OPC mixes. They are using other cementitious, but they're already, some of our pours have been at half the national average GWP before our carbon goes in. We call this benefit stacking. I like to say you would never buy a pair of hiking boots that are all made by Vibram, right? You want a Vibram sole, you want a Solo leather, you want Gore-Tex fabric. We're the Vibram. Go find Gore-Tex fabric or go find good leather somewhere else to put together into this shoe, right? So we're just one part there. In a soil environment, there's a certain percentage of the carbon that is based on the H to C ratio, the hydrogen to carbon ratio in the finished biochar, said to be durable. There's an assumption that a certain amount oxidizes, a certain amount gets eaten up, et cetera. A certain amount changes chemically from weathering. All of that is minimized to an incredible amount, if not fully, in the concrete matrix. And even if a building lit on fire, the concrete is not going to hit these temperatures, right? It's in that matrix. Even if you crush that concrete, you're not going to change anything. You're going to expose it to the air, maybe, but it's not going to change what would be in a soil environment, let's say. So it's extremely durable. Our HC ratio is very low, so we have high permanence in the multiple centuries to thousands of years. The science kind of breaks out to an unknown at a certain point as an inertness. And then when you're binding that in the concrete matrix, you're sort of throwing all questions out of the window. Yeah.
Cool. All right. This was amazing. This was really worth the extra few minutes. Activists out there, people who are locally, take this video and send it to people that you know within the city. You can reach out to Garrett. He gave us contact information. I am going to reach out to the authors of that UC Davis paper and see how quickly I can get them to actually come onto this CDR and talk about that paper, because that is a massively high number to make through peer-reviewed, not just a peer-reviewed journal, but science. So we need to really, really look at that. That is extraordinary. Garrett, thank you so much, my friend. That was phenomenal. And we'll be talking, you and I, very, very soon. And hopefully I'll see you in New York for Climate Week. With that, everybody, I'll bid everybody adieu and see you in a couple weeks.
Thank you, everyone. Have a good one.